This is going to be a lesson on student learning task 5. We're going to define a complex number and determine its relationship to the real number system. So what I'd like everyone to do is to write down numbers 1 to 7 and complete as many of them as you can using your knowledge about the imaginary number. So hopefully everybody got that I squared, that's just -1, because as a reminder, I squared is going to be the square root of -1 squared, which is just -1. So now for I to the third, we can rewrite that as I times I times I to the third, which is the same thing as I squared times I. And we know that I squared is -1, so we have -1 times I, which gives us -I. Now I'm going to continue this idea of just like expanding these out. Go ahead and try them if that like helped jumpstart your memory. Pause the video, try them on your own. You can always change the speed to check your work. So I to the fourth, if I have I to the fourth, that's going to be like I squared times I squared, because I know that when I multiply like bases, I can add the power. So that's how I can separate I to the fourth into I squared times I squared, because 2 plus 2 is 4. I know that the first I squared is -1. The second I squared is -1. And then -1 times -1 gives me 1. Now that I've established that I to the fourth is 1, that's really going to be key in doing these last 4, because I can separate I to the fifth as I to the fourth times I to the first, just like I did up here. Remember, when I multiply like bases, I can add their exponents. So here, 4 plus 1 is 5, and then I to the fourth is 1, and I is just I. I'm going to use this technique all the way down, and I really like this I to the fourth being 1. So I'm going to go I to the fourth times I squared, I to the fourth times I to the third, I to the fourth times another I to the fourth. Go ahead and simplify those if you can on your own. Okay, so for number 5, I to the sixth, separating that to 4 plus 2, I to the fourth is just 1. And I know that I squared, well, that's just -1. And so 1 times -1 is -1. I know I to the fourth is 1. So at this point, every time I have an I to the fourth, I'm just going to make that a 1. Now, I to the third, I did up here, but just as a reminder, that's going to be like I squared times I, because 2 plus 1 would give me the 3. Those exponent rules, man, they just never go away. I squared is -1 times I makes I to the seventh -I. And then I to the eighth, well, this is just 1 times 1. So I want you to take a look at these 7 problems, and I want you to see if you could think about how could I do a really, really hard problem. Like, let's say I had I to the, we'll go with 49th. If I wanted to evaluate I to the 49th quickly, how could I do that? Well, one way you can do that is you can find the highest multiple of 4 that comes out of 49. This is what I mean. Like if I divide 49 by 4, I would have a remainder here. So I'll be honest with you guys, I forget how to spell the word separate. So I'm going to say split, actually. That's better. I know how to spell split. I can never remember if separate has an E or an A. S. Split the exponent into the highest multiple of 4, and then whatever's left over. And if we say leftover, that's kind of sloppy. And we'll say the remainder. That's a nicer word. So when I look at 49, that one's not hard. I know the highest multiple I can take out of 49 is 48. So I'm going to go I to the 48th times I to the first, because like 48 plus 1, 49. Now I know that any multiple of 4, like this I to the 8th was just I to the 4th times I to the 4th, And I to the fourth we know is 1 because of right here. Like this is like money in the bank right here. This is the important one. So I know that this is going to be the same. So it's just going to be 1 times I to the first, which is just I. So what I'd like you to do is to please pause the video, and I have 4 more problems that I would like you to apply this technique to. Again, you're going to pause the video, work on these 4 problems, and then unpause the video and check your work with mine. So I would like you to please try these 4. Go ahead and pause the video now. Okay, so you should have tried these 4 on your own, and I have this first one is kind of a fun one, 402. So I to the 402, I'm going to separate that into I to the 400 times I squared. And I know that any multiple of 4, that's just going to be 1. And I want to remember that I squared is just -1. And as a reminder, I'm going to write this maybe one more time. If I have I, that's the square root of -1. So if I have I squared, boop, boop, ta-da. So 1 times -1 is -1. Then we have I to the 25th. I'm going to separate that. I think the highest multiple before I go over 25 is 24. So I have I to the 24th times I to the first. So it's going to be like 1 times I, which is just I. Then we have I to the 51st. I think 48 is our closest multiple. So I to the 48, and there are 3 left over. And I'll be honest with you, if I to the third is like creeping you out a little bit like that, I'm not asking you to memorize anything. We know that I to the 48th is 1 because all we need to remember is this guy, I squared is -1, and anything to the 4th is going to be 1. So now I to the third, 1, 2, 3. Oh, these 2 together, I times I, that's our I squared. I squared is -1. So we have 1 times -1 times I becomes -I. And then for our last one, I to the 80th, well, that is a multiple of 4. Anyone that is a multiple of 4 automatically is just going to be 1. So some announcements. We do have homework. It is due Sunday. If you are the 7th period class, which is who's watching this video as their lesson, your quiz is Monday. So if you are 7th period, if you're a B-day student, if you are watching this video just for fun and you're an A-day student, your quiz is due Sunday. Now, as a reminder, this quiz is not just on imaginary numbers. It will cover the lesson before break. So this is the lesson right here on solving radical equations. So make sure you review that in addition to the work we've done this week with imaginary numbers. Okay, so this is all what the quiz this weekend is on. Okay, so these are the answers to Monday, Tuesday's homework. They were posted on Google Drive. If you need to pause the video to check your answers, obviously these should be in your own words. And if you submitted my words, then yeah. And then here are the answers to the solvings at the bottom. Those are the problems. So here we go. Today, we're really going to focus on different number groups. So I just have a few more. Again, just go ahead, pause the video real quick. Let's just power out 8 more of these to make sure we're solid. So pause the video and then unpause when you're ready for me to go over them. Okay, so like I said, you should have done these on your own. I to the 29th, the highest multiple of 4 is 28. Ooh, I forgot the I. I to the 28th times I to the first, because 28 plus 1 would be 29. I to the 28 is just 1. I is just I. Number 2. All right, well, normally I would think 48, but that's too big, so I'm going to have to go 44. 44 I to the third. and then this becomes a 1. And now we're going to remember that I to the third is like 1, 2, 3. These two make -1. So I have 1 times -1 times I becomes negative, oops, I. That's ugly I. That's better. All right. Number 3, I to the 12th. Well, 12 is a multiple of 4. So I know this one is just 1. And while we're at it, I know that 16 is also a multiple of 4. So that one's just 1. And these guys aren't multiples of 4, so we're going to have to dig those around. 82, 80 is our multiple. So I'm going to start with I to the 80th times I squared. I to the 80th is 1. I squared is -1. 1 times -1 is -1. Number 6, I to the 33rd power. My multiple of 4 is going to be 32. And 1 left over. So 1 times I is just I. I to the 18th. My multiple of 4 is going to be 16. I forgot to change colors. Sorry. And then I squared. I to the 16th is 1. This is -1. And then I to the 43rd. My multiple is going to be 40. And then I to the third. And honestly, guys, yes, if you've memorized that I to the third is -I, that's cool. But some people haven't, and that's all fine also. There's no reason to memorize extra. If you want to write these out and be like, hey, look, I squared -1. That's fine. 1 times -1 times I becomes -I. What I also want to do on this page is talk about reducing radicals with I. I want to point out some common mistakes. So if I have a problem like number 9, I need you to fight the instinct of multiplying the -2 and the -5. That is a really big instinct kids have, and you need to fight that. Don't just make this the square root of 10. This is what we need to do. We need to reduce this square root of -2 as the square root of -1 times the square root of 2. Because I need to recognize that these were originally negative radicands, negative numbers under my radical. So I'm going to separate the root -2, and I can do this because I am allowed to multiply and divide under a radical based on the laws of exponents. I'm going to split the square root of -5 to the square root of -1 times the square root of 5. So now here, this root -1 is I, and the root 2 is still root 2. This square root of -1 is I, and the root 5 is still root 5. Now, I times I becomes I squared. The square root of 2 times the square root of 5 becomes the square root of 10. Now, I squared, I know is -1, so my final answer is going to be -1 root 10, or just -root 10. This negative outside shows that my two original radicands were negative. So why don't you go ahead and pause the video and try number 10. Hopefully you tried number 10 on your own. Again, you should have paused the video and tried it. If you didn't, pause the video, try it. And you separated the square root of -3 into the square root of -1 times 3. And then the square root of -8 becomes, okay. Then square root of -1 becomes I. Also I. I times I becomes I squared. 3 times 8 is 24. And then I squared is -1. So we have negative square root of 24. Now, if you left this as your final answer, that would be 100% fine. However, I want to recognize that it is very common to see this root 24 reduced. This is what I mean. We can multiply under a radical. So I can separate 24 into the perfect square of 4, and then the not perfect square, 6. Okay, 24 is 4 times 6. The square root of 4 is 2. So you might see this written as negative 2 root 3. Now, both of these answers are acceptable. I point out the reduced version because on standardized tests like the SATs, they're not going to give you an answer like the square root of 24. You will most likely see 2 root 3. So I want to show you that. However, this negative square root of 24 is a correct and acceptable answer. Hopefully you noticed that number 11 is a little different from 9 and 10. It's an addition problem. So I'm going to separate, and these are also perfect squares. So like when I separate these, I'm going to separate them a little differently. I'm going to put the 9 first because that way it's like the square root of 9 and this times the square root of negative 1. And then the square root of 9 we know is just 3, and then this is I. Here I have the square root of negative 100. Again, I'm not going to separate it like I did in 9 and 10 because this is a perfect square. I'm going to put the perfect square number first in my scratch work. The square root of 10, I'm sorry, the square root of 100 is 10. And then the square root of negative 1 is I. And now we have like terms here. 3i plus 10i is 13i. So there are going to be a couple of these in your homework tonight. Please make sure you refer back. Oops, wait, there's a typo here. There should be a 6. I don't know why I wrote a 3. Sorry. Make sure you refer back to these 3 problems. So the other thing we're going to do today is we are going to look at the real number system and how it relates to the complex number system. So hopefully you printed this out. If not, take a minute, pause the video, carefully recopy the diagram. Okay, as a reminder, complex numbers are defined in the form a plus bi. That's our standard form where a and b are real numbers and I is the square root of negative 1. A is the real term, bi is the imaginary term. If there is no real term, it is called a pure imaginary number. If there is no imaginary term, it is called a real number. If we have both parts, it is called a complex number. So in the space below, we are going to complete the graphic organizer to represent relationships among numbers in the complex number system. So we have several different types. We have complex, we have imaginary, real, natural, integer, whole, rational, or irrational, and rational. And we're going to work from the outside, from the inside out. We're going to start with, and I like to work in rainbow order because it's just more fun. We're going to start with natural numbers. Natural numbers are going to go in this innermost circle. And those are what I like to call the kindergarten counting numbers. Like when you first were in kindergarten and you learned how to count, how did you count? You counted 1, 2, 3. These are our Sesame Street numbers, okay? Counting numbers starting with 1. Well, then at some point, you were introduced to the concept of 0. So now we have the group of whole numbers. That's the next circle. Now, everything that's natural is also whole because see like how the natural number circle is within the whole number circle. So the only number that's not natural, that's whole, is the number 0. So whole numbers are 0 plus all the natural numbers. Then we have the integer numbers. The integer numbers are commonly referred to as positive and negative whole numbers, and that's exactly what they are. That is really bad handwriting, Strauss. Let's try again. Better. So the integer numbers are going to include 0. They're going to include 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're also going to include negative 1, negative 2, negative 3, all the negative versions of these whole numbers. So now we have, this is what I call like the middle school numbers. This is the numbers you worked a lot in middle school, the integers. So outside of the integers, we have the rational numbers. And rational numbers are important. I'm going to remind you here that a rational number, and I would write this down, rational numbers are any number that can be expressed as the fraction of integers. It does not include all decimals, okay? It includes decimals like 0.3 repeating. Let me label this up. This is rational. Okay, 0.3 repeating. So if I have like 0.3 with a line over it, that's like 1/3. That's the fraction of integers. Like if I had negative 0.1, that would be negative 1/10. That's the fraction of integers. If I had, let's see, we'll go with, I don't know, like 0.24 or 0.25. Sorry, I don't know why I said 4. Maybe I was thinking about that being 1/4. All right, anything that I can write as the fraction of integers works. Like if I have negative 0.6 repeating, that's like negative 2/3. If I have 0.1 repeating, that's 1/9. These are all rational numbers. If you can write it as the fraction of integers. Now, some people now start to argue, well, what about just 4? Well, 4 can be written as 4/1. Therefore, all the integers now can be written as the fraction of integers because you just got to toss them over 1. Then in this lonely circle outside here, if something's not rational, that means that it is irrational. And our irrational numbers, you guys like the number pi, that is irrational. An irrational number is a number that is real but cannot be expressed as the fraction of integers. So pi and e are some of your favorites. My personal favorite is the square root of 2. Square root of 2 is my favorite irrational number. We should make that like a bonus. Not really. Negative root 7. If you had, 2 plus or minus the square root of 5, these are all irrational numbers, okay? Now, together, the irrational numbers and the rational numbers, they make up the real numbers. And I honestly have a problem with this diagram. And if I'm in my room, I normally like redraw it a little bit, but I don't know, wasn't feeling it today. There is nothing in this space, in this like space here, like there's nothing here. Okay, there's no number that's real that doesn't classify as rational or irrational. Okay, so this box that represents the real numbers, everything has to fall either as rational or irrational. All right, so this like space is just to write the words real numbers, but every real number gets classified as rational or irrational. You cannot be in a real number without being rational or irrational. Now in this box, we're going to put our pure imaginary numbers, but not in that color. We'll use brown. Now, pure imaginary numbers only exist in our imagination. There is no real part to them. So for example, I, 2i, negative I root 5. All of these are pure imaginary numbers. Remember, they don't have an a. So it's almost like it's like 0 plus 4i. There's no real component. So in this large box that makes up the whole diagram, what this is, this encapsulates every number. This we're going to label as our complex numbers. So every number can be classified as a complex number. There are 3 boxes we can put a complex number in. A complex number can also be a real number. A complex number can also be pure imaginary, or a complex number can just be complex. For example, if I have 2 plus 3i, that's not a real number because it has the 3i. It's not pure imaginary because it's got the 2. It can only be classified as complex. Like if I had one, I'll make something crazy up. Like if I have 1/2 plus I root 3, same thing. It's got a real part. It's got an imaginary part. If I had negative the square root of 3 minus 4i, all of these numbers can only be classified as complex because they have a real part and they have an imaginary part. What I would like you to do, keeping this diagram, handy, is I have a set of numbers, and what I want you to do is give the numbers the most specific classification. So for example, if I gave you the number -7, let's examples. So if I gave you -7, and I'm like, what is the most specific classification? You would say integer. If I gave you the number square root of 5 and asked for the most specific classification, you would say irrational. So I'm going to give you a set of numbers and I want you to give me the most specific classification. So here are your choices. Here are our numbers. I don't know why that last one's empty. I guess whoever made this just couldn't come up with the last problem. But go ahead, pause the video, and sort these numbers. Give each number its most specific classification name. Okay, at this point, you should have paused the video, and all these numbers should have labels. I'm going to reveal the answers and go over some of the ones that cause people the most difficulty. So here are the correct answers. I am assuming we are good on integer. We are good on rational because I can write this as 1/2. This one is also rational. 0.4 repeating, I want to say is 4/9. I don't know, let me check. Yeah, I was right. It was 4/9. Because I figure 0.1 repeating is 1/9. So multiplication. All right, so this one's also rational. And people are like, but it's a weird decimal. Well, it's really not. Tens, hundreds, thousandths. I have 349 over 1,000. Ta-da, fraction of integers. This one is natural because it can just become 5. Natural, whole, rational. Shouldn't have too many problems there. Our favorite irrational, pi. Clearly irrational, root 13. Clearly rational, 2/3. This one, some people might write it down as rational, but then if you take a look at it, -10 over 2 is just -5, making that line integer. 5 is obviously natural. 2.25 is obviously rational because this is just like 2 1/4, or you could write it as 9/4. There we go, fraction of integers. This is integer because it's -5. This is natural because it's 3. Pure imaginary, integer because I squared is -1. Complex, it's got a real and an imaginary component. Now this one, I would personally prefer to write it -2 plus 4/3 I, because I like my numbers in standard form, So this is obviously complex. It's got a real and it's got an imaginary. 5i, pure imaginary. It only has an imaginary component. Same with -2i. Now, this messes people up and they want to write it as complex, but there's no I on the root 2. It just so happens that this irrational number has an integer being added to it, or it's being subtracted from an integer, but it is still irrational. I cannot write this as the fraction of integers. However, it does not contain an I. Therefore, it falls in the irrational category. All right, your homework tonight is to simplify the following And then also to do some classifications. This assignment is posted in my MCPS, and the answers will be posted in our daily class notes on Google Drive.